Ice exists in various forms and covers about 16% of the Earth's surface, accounting for up to 33% of the land area during the peak of the Ice Age in the Northern Hemisphere. Glacier, coastal zone, permafrost, ice and snow play an extremely important role in Earth's climate. They reflect the energy back into space. Ocean currents shape and create different weather patterns. But there are signs that Earth's vast ice reserves are gradually disappearing. Scientists are drilling deep into the ground in Bang to explore the future of Earth and study the evidence of past climate change in ancient seabeds. They are uncovering the mysteries of humanity's fate over the next 1,000 years and even the centuries beyond. About 30,000 years ago, Earth began to plunge into an extremely harsh winter. The rivers in the state flow into what was once a temperate region, causing the melting ice to expand beyond the polar seas. New layers of ice are gradually forming across the vast icy plateau of Greenland and spreading throughout the Antarctic continent. These ice masses are enormous blocks of ice, formed over successive glacial periods spanning millions of years. However, scientists are now questioning, are they truly as durable as we once believed? Since the Industrial Revolution, the global average temperature has risen by at least 1 degree Celsius. By the end of this century, temperatures could rise by 1 to 3 degrees. When temperatures rise, ice melts faster and sea levels also rise. West Antarctica, a vast region larger than Mexico, is considered an exceptionally vulnerable area. If it breaks apart, the amount of ice contained within is enough to raise global sea levels by at least 4 meters. Greenland is also showing signs of melting, particularly in areas where glaciers formed from thick inland ice meet the ocean. That ice mass alone contains enough water to raise global sea levels by 7 meters. In the coming decades and centuries, rising sea levels could threaten the homes and livelihoods of a quarter of the global population. With so many potential dangers, scientists are closely monitoring the icy regions on Earth. With the aid of satellites, military radar, and deep ice core drilling expeditions, scientists are reconstructing past climates, searching for clues about the future development of Earth. It turns out that the cycles of melting and freezing were pivotal events in Earth's formation history. Over 2 billion years ago, Earth experienced at least 5 ice ages or glacial periods. These cold periods, along with the subsequent warm phases, were influenced by multiple interconnected factors. Convection events, the evolution of plants and animals, ocean circulation patterns, and the shifting of continents. The world as we know it today began to take shape between 50 and 90 million years ago. At that time, the continents were gradually shifting to their present-day positions. The Americas have separated from Europe and Africa. India is increasingly integrating more deeply with the Asian region. The global climate is getting warmer. About 55 million years ago, Earth's temperature suddenly soared. In just a few thousand years, the temperature has risen by about 5 degrees Celsius. The CO2 concentration has risen to approximately 1,000 ppm, parts per million. This number has risen to 400 today, compared to just 280 a century ago. But the situation had clearly begun to ease. The shifting continental plates separated the Arctic from the vast oceans. This creates conditions for a layer of fresh water to settle, while also enabling the aquatic plant known as duckweed to thrive. Each year, 1 hectare of forest can absorb up to 15 tons of CO2. During this process, the Indian subcontinent collided with the Asian continent, forming the majestic Himalayas. During the weathering process, rainwater that comes into contact with exposed rocks absorbs large amounts of CO2 from the atmosphere, then transports this gas to the ocean. When the level of CO2 in the air decreases, the temperature also gradually drops. In early records of the recent hunting period, scientists were able to unexpectedly identify the agent causing climate change. Serbian scientist Milutin Milankovic was the first to describe this phenomenon in the 19th century. He realized that cyclical changes in Earth's movement altered the amount of solar radiation reaching the poles. To summarize, approximately every 100,000 years, these changes cause the Earth to enter a cooler climatic period with widespread ice coverage. Each ice age is followed by an interglacial period, when rising temperatures cause the ice to gradually melt. Milankovic cycles alone are not strong enough to drive the variation. They started by setting everything up. The amount of sunlight reaching the Arctic decreases, causing sea ice to form in winter and persist throughout summer. Next year, the court's jurisdiction will be expanded. Due to their ability to reflect more solar energy back into space, cooler oceans can absorb more CO2, thereby reducing the greenhouse effect. Conversely, when ocean temperatures rise, the amount of CO2 released into the atmosphere also increases. Here, CO2 traps more solar energy. Scientists are studying past climate changes to find clues about what may happen during the current period of global warming. Today, Greenland is regarded as a vast laboratory for exploring Earth's history. The landscape and fjords recreate the story of mountain formation, volcanic eruptions, ice ages, and the evolution of living species. Originally located in the southern hemisphere, Greenland gradually shifted northward and now belongs to the North American region while maintaining historical and cultural ties to northern Europe. The mountain ranges running parallel along the eastern and western coasts were formed from ancient bedrock dating back approximately 300 to 400 million years ago. Recently, the thick ice between the mountains has melted and drifted away, while the glaciers continue to erode and encroach upon the land. To assess the variability of the ice layer, scientists combined the use of aircraft and satellites to observe large-scale changes. Using the GRACE satellite, scientists have tracked the rate of ice melt worldwide. The dark pink areas indicate regions with the greatest ice loss. From 2003 to 2009, this island lost approximately 1 trillion tons of ice, primarily along its coastlines. Researchers are particularly concerned about a large group of glaciers located near the shore. Before flowing into the sea, glaciers pass through a series of narrow mountain crevices. These crevices act like dams, holding back the mass of ice behind them. Calving, the Jakobshavn Glacier flows into the western coast, releasing approximately 35 billion tons of ice into the ocean each year. The Jakobshavn Glacier is currently the fastest-moving glacier in the world, flowing into the sea at a rate of 17 kilometers per year, 3 times faster than its recorded speed in the mid-1990s. Then, in the northeast, there is the massive Zayaj Glacier, once considered the last remaining stable glacier in Greenland. This glacier flows through the center of the inland ice sheet along the northeastern coast. Between 2003 and 2014, the ice retreated approximately 20 kilometers and lost 10 billion tons of ice. There are many signs indicating that the melting process may occur faster than expected. In the summer, meltwater often pools on the surface, forming small ponds between ice sheets. This area lies just south of the Jakobshavn Glacier. As these meltwater ponds grow deeper, water can flow down through cracks in the ice. This process may accelerate melting by transferring heat to the base of the ice sheet. When this phenomenon occurs, the friction between the rock layer and the overlying ice decreases, causing the flow to accelerate. Greenland is losing ice at an increasingly rapid rate. If the entire ice sheet melts, much of Greenland's territory will be submerged underwater. As the ice on small islands gradually melts over time, the land in those areas will slowly rise due to reduced pressure. Meanwhile, the massive ice sheet from the continent exerts a strong gravitational pull on the surrounding ocean, causing a significant local rise in sea levels. It's ironic that if the ice melts to its maximum extent, sea levels could actually drop by about 1,000 kilometers. Meanwhile, more distant coastal regions would face an average sea level rise of over 7 meters. Just how much will Greenland melt? Among all the previous interglacial periods, the most well-known is likely the most recent one, approximately 130,000 to 115,000 years ago, also called the Eemian period. At that time, atmospheric CO2 levels were comparable to pre-industrial levels, and global temperatures were only slightly higher than today. Notably, regions that are now Arctic tundra once hosted forests during that period. The 19th-century Dutch scientist who discovered this period noted that fossils of mollusk species appeared further north than their current distribution range. Today, scientists assert that the increasing levels of solar radiation have significantly impacted the northern hemisphere, causing a sudden spike in Arctic temperatures. This excess heat is absorbed more intensely by ice-free ocean regions in the vast northern forests. The global consequences of this phenomenon could lead to a sea level rise of 4 to 8 meters above current levels. Scientists have carried out one of the deepest ice drilling projects in history to determine the amount of ice melting from Greenland's ice sheet. The ice drilling project in northern Greenland, also known as NEAM, has collected ancient ice samples. These specimens tell an incredibly surprising story. If you visited Greenland during its warmest period in history, the temperature back then would be about 8 degrees Celsius higher than it is today. However, during its coldest period, the temperature would only drop by about 25% compared to that. Therefore, Greenland can only contribute a maximum of 2 meters to the rise in sea levels. A 1-meter rise in sea level could stem from the thermal expansion of seawater due to rising temperatures. So what is driving the accelerated melting of ice? Ice and 70% of Earth. If you could turn back time 250 million years, you would see that what is now the icy continent of Antarctica was once a warm land with dense forests and winding rivers. In this warm and humid world, diverse plants and animals thrive together. At this stage, known as the Pome period, Antarctica was located at the southernmost tip of the massive supercontinent called Pangaea. At that time, Antarctica basked in the warm sunlight of the tropics. As the supercontinent Gondwana began to break apart, Antarctica gradually drifted southward as part of this massive landmass. About 130 million years ago, a series of cracks formed in Earth's crust, causing the supercontinent Gondwana to break away from South America and Africa. Australia finally broke away completely around 85 million years ago. Later, Antarctica also separated independently, between 65 and 50 million years ago. Warm weather is giving way to cool, dry conditions worldwide. In the southern regions around Antarctica, conifers and other cold-resistant plants have thrived. In some regions, the landscape has transformed into tundra. The ice around the South Pole gradually accumulated, forming a dense ice sheet. At the same time, strong winds blowing around the polar region from west to east accelerated the ocean current circulating this area. Known as the world's strongest ocean current, it plays a role in shielding the continent from the northern tropical waters. The combination of multiple factors has influenced Earth's climate. The decline in CO2, the isolation of Antarctica, and the trend of permanent ice sheets reflecting more solar energy back into space. About 2.5 million years ago, Earth entered its last ice age, the Quaternary period, the epoch we are living in today. Year after year, whenever storms sweep across the ocean, they blanket Antarctica in layers of pristine snow and ice. Currently, this is the windiest, driest, and coldest place on Earth. There is no ordinary residential community here, only a few thousand scientists and their support teams living in scattered research stations. In July 1983, scientists at Russia's Vostok station recorded the lowest natural temperature ever measured. With a temperature of -89.2 degrees Celsius, a recent study based on satellite data recorded an even lower temperature, reaching -93.2 degrees Celsius. The small amount of snow here will accumulate, causing the mass of this land to gradually increase. You can clearly see evidence of this in the thickening snow and ice at the Antarctic Research Station. The roof of this geology room was built in the 1970s. By 2009, when it ceased operations, the entrance had almost been completely buried. Beneath the 4 kilometers thick ice covering this outpost, there's no hope of it melting anytime soon. Part of the reason is that the underground mass was detected using special radar imagery. The eastern part of the continent in the image is the stable core of the continental crust. Conversely, the western side is 2,500 meters below the current sea level. The Amusel coast is witnessing an increasingly rapid rate of ice melt. Let's take a look at how much ice has been lost. This is a reconstructed image of the continent during the last ice age, approximately 20,000 years ago. Compared to the current image, the low flow in the western sea area has changed significantly. The glaciers on the continent are gradually moving toward the ocean at an average speed of about 100 meters per year. They will drift onto the icebergs, stretching far out into the open ocean. When ice shelves like these expand, they become more prone to cracking. Recently, a massive crack has appeared on the Vin Island Glacier. In 2 years, a 720 square kilometer iceberg broke off. Scientists are paying increasing attention to the hidden dynamics beneath these shelves. Recently, the southern sea region and continental shelf have been warming at a rate of 0.2 degrees Celsius per decade. This trend is considered one of the most puzzling developments in the story of climate change. In recent Arctic summers, the period of sea ice melting has lasted longer than before. The minimum sea ice area has been continuously shrinking, while the remaining ice has also been thinning by more than 1 meter per year in some regions. Conversely, the area and thickness of sea ice in Antarctica have been steadily increasing. Another possibility is that the strong polar winds could push the ice together into denser, more resilient masses. Another hypothesis suggests that the meltwater formed a widespread layer of cold freshwater over the coastal sea, where favorable conditions made it easier for the water to freeze. Here is satellite cracks observation of the latest changes across continents. The area of lost ice is shown in pink and red. The color blue indicates an increase in ice. The most severe damage is concentrated in the western part of Antarctica. Notably, this is where a series of fast-moving glaciers flow into the Amur Sea. European scientists have confirmed this trend using radar data from the Riosat satellite, while monitoring changes in the elevation of Antarctica's ice sheet. The study shows that from 2010 to 2013, this continent lost an average of 159 billion tons per year, a 31% increase compared to the previous period. As early as the 1960s, some scientists had already raised warnings about this issue. One of the reasons they cited is that the winds blowing around the continent are growing stronger. As the temperature difference between northern regions increases, these winds also become more intense. The brave monkeys who dared to venture into the open sea once saw the Southern Ocean as the fastest route to travel around the world. Today, stronger winds have taken effect, pushing the warmer water layer to the surface, which typically occurs naturally in the deep waters of the Southern Ocean. These warm waters are gradually weakening the ice shelves that extend from the inland glaciers. Satellite images taken over a decade ago clearly show the consequences this phenomenon can cause. On the Antarctic Peninsula, the Larsen ice shelf extends into the sea. A photograph taken in early February 2002 captures the moment Larsen began to crack. By March of that year, the ice shelf had collapsed. Countless icebergs came crashing down into the sea. Without the ice shelf to hold them back, the glaciers behind began flowing faster, pushing an additional 27 cubic kilometers of ice into the ocean each year. This was not a rare phenomenon. Many other places were witnessing the same thing. A research team established a base on the Vin Island Glacier, originating from New Southampton emission. From the surface, they drilled 500 meters deep into the ice layer to observe changes in temperature, hardness, flow, and volume. The results show that warm water is eroding the base of the ice shelf at a melting rate of approximately 6 centimeters per day, equivalent to 22 meters per year. Another research team used satellite radar and airborne radar to monitor these changes on a regional scale. The color red indicates the areas where glaciers are moving the fastest, particularly the points where ice flows into the ocean. Now, observe the places where glaciers push out to form ice shelves, such as in Da Vin. Here, the flow speed of the glacier is steadily increasing. The most noticeable changes have been recorded at Smith Glacier, one of the smallest in the group. Back in 1996, this area was precisely where ice and land met beneath the bed of Smith Glacier. By 2011, the green road mentioned below had retreated 35 kilometers inland, equivalent to a withdrawal rate of over 2 kilometers per year. Now, the ice sheet covering the continent is gradually disappearing. The red areas indicate the regions with the strongest flow, where you can observe glaciers moving rapidly through narrow valleys, some of which lie deep below sea level. As the coastline retreats further, more seawater floods into the subglacial basins beneath the ice. For most glaciers, there are no major obstacles like hills or mountains that can stop them once they start moving. The faster a glacier flows, the greater the risk of the ice behind it collapsing. If this happens, the cause may not be entirely due to climate change. Scientists observed that the water flow beneath certain glaciers is moving too rapidly to be caused solely by seawater. The Transantarctic Mountains, which divide East Antarctica and West Antarctica, were formed by the phenomenon of water slipping occurring in the tectonic plate beneath. Scientists have recorded seismic activity consistent with the movement of magma within the Earth's crust at a depth of 25 kilometers. Currently, scientists have discovered a significant amount of geothermal activity beneath one of the largest glaciers, generating real heat that is causing the ice to melt faster. To date, most research on future sea level rise has focused on the ice sheets in Greenland and West Antarctica. Combined, they could cause sea levels to rise by up to 12 meters. The vast ice sheet in East Antarctica has largely gone unnoticed due to its immense scale and year-round frigid climate. This region appears largely unaffected by the warming trends occurring in the northern areas. A recent study has led scientists to question the true stability of this region. If there is any area in East Antarctica most vulnerable to impact, it is Wilkes Land. Under the current pressure of glaciers, some areas of this continent lie more than 2 kilometers below sea level. The amount of ice accumulated here is enough to raise sea levels by an additional 3 to 4 meters. Currently, the Wingcatlet ice sheet is assessed to be in a state of equilibrium, meaning the ice that melts or breaks off into the sea is offset by new ice forming inland. So what could cause Wingcatlet to lose this equilibrium? One crucial factor is the area where the ice sheets are pinned against a series of underwater mountain ranges on the seafloor. These mountains act as barriers, preventing the glaciers and the ice behind them from flowing forward. If warm water erodes the ice resting on these submerged ridges, the ice can begin sliding into the ocean. This effect is likened to tilting an upside-down water bottle. Pull out the stopper, and gravity will make the liquid spill out completely. Once the ice starts drifting, there's no way to stop it. Is this scenario even possible? On the smaller Pinkstone Glacier, scientists have discovered more ice chunks breaking away from the underwater mountain range. The melting of Antarctica's coastal glaciers is a process spanning centuries. However, once this phenomenon occurs, sea levels will continue to rise steadily in the near future. A recent study analyzed changes in Antarctica during two distinct periods, the Liu-Chen period 3 million years ago and the subsequent Imian period. Based on the current rate of ice melt in Antarctica, the study predicts that sea levels could rise by more than 2 meters by the end of this century. By the year 2500, the continuous melting of ice in Antarctica could cause sea levels to rise by more than 15 meters. Alarmingly, even if greenhouse gas emissions are controlled, the excess heat already trapped in the oceans may continue to melt ice for centuries. This consequence will profoundly impact human lifestyles for the next 100 or even 1,000 years. The changes in our daily lives are primarily shaped by upcoming events. In the fields of technology, politics, and culture, major cities like New York, London, Hong Kong, and coastal urban centers worldwide have continuously evolved and developed over centuries. In the course of their history, rising sea levels could threaten their existence in just a relatively short period of time. Additionally, coastal communities and businesses were wiped out, forcing hundreds of millions of residents to migrate further inland. The story of melting ice and rising sea levels often involves many unpredictable factors. Amid the dramatic yet obscured developments veiled in rational scientific language, critics have focused on analyzing the margin of error, an inevitable characteristic of the scientific research process. There are many conspiracy theories surrounding the undermining of computer simulations' predictive power, along with flawed policies in legislative debates. Time passes, and our choices grow ever fewer. The massive ice sheets on Earth hold within them stories of history, and these are invaluable lessons for our modern era. In the context of rising CO2 levels and Earth's temperatures, rapid ice melt is causing significant sea level rise. What threats will this pose to our planet in the coming centuries and millennia? Could this world, the very one that has sheltered and nurtured us, truly be the world as we once knew it? The Earth will endure forever, ceaselessly transforming with each passing moment and stretching across time, like a planet brimming with vitality.